In this video, we are going to talk about how to recognize handwritten digits using NumPy only. We are going to use the MNIST dataset, which is a very popular and famous dataset. There are a lot of tutorials of lectures teach us how to recognize a digit in MNIST dataset. However, the special thing about this lecture is that we are going to use NumPy alone. Of course, we are going to use something like Pillow to display image, or maybe we are going to use Python standard library to download the dataset files. What I mean is for the more intelligent part or more machine learning part or algorithm part for things that actually contribute to recognize the handwritten digits, we are going to use NumPy only. We're not going to use something like a scikit-image, scikit-learn, or OpenCV, or maybe even PyTorch or TensorFlow. We use NumPy and its functionalities only. So that you can see by combining some functionality of NumPy, you can already do something really powerful and really fast. Without further ado, let's begin. So let's first load some necessary libraries like Pillow and NumPy, and we're going to download the files. I'm using the URL retrieve in the Python standard library, and I'm customize a report hook to display the progress of downloading. We're using the original file format for the MNIST. Because MNIST is so popular, a lot of people convert the dataset into different formats. Like you may see something can be loaded using Pico, Python's Pico, or other like NumPy set file format. However, in this lecture, we are going to use the original file format, which is custom ad hoc file format. By loading this kind of arbitrary binary file format, we can demonstrate some functionalities of NumPy to load arbitrary binary files. But before that, let's download the files using the customer code for downloading files. So we have 4 files to download. Each has a file extension IDX3 or IDX1. You don't have to look for internet to search for this file format, because this format is only used for MNIST dataset. Okay, so because I have already downloaded the dataset files, so because I want to demonstrate the download process, so let me do some small hacks right here to force it to download the files again. So you can see this is our download code. This is our customized downloader. Okay, so you can see that we have 4 files, 2 for testing dataset and 2 for the training dataset. And for each part, it contains 1 file for the image of these handwritten digits, and 1 file contains the corresponding labels of these handwritten digits. So what is exactly the file format for this IDX file? According to the website of MNIST, the description of the file format is at the bottom of that website. It contains only 1 web page, and this description is at the bottom. The file contains 1 magic number at the beginning. The magic number consists 4 bytes. The first 2 bytes are always 0, so that you can check whether it is actually the dataset files of MNIST. Because if the first 2 bytes is not 0, then we can show you have done something wrong. Maybe you didn't decompress the files, or maybe you download a wrong file. So they have no meaning. It's just kind of like signature. The third byte denotes the type of the data. So basically, each dataset can be considered as higher dimensional array. So recall that for a high dimensional array, we only care about the D type and the shape. We care about the D type and the shape. That's the first thing we need to observe, or that's the first information we wish we can obtain. So you can see that the third byte corresponded to the D type, and it has arbitrary code for each D type. In fact, we are going to use only the on-site byte, so it should be just 8. And the fourth byte code is numbers of the dimension of this high dimension array. So first of all, we should just read this 4 bytes. How do we read these 4 bytes? We can use Python's OpenFile API to do so. But NumPy also contains some functions so that we can read arbitrary binary file and make it becomes a NumPy array. So first of all, we read the file. So this is the file name. Let's get just one file name here. File is equal to this guy, train image ID x3 ubyte. So let's read the first 4 bytes and see what's there. So the first 2 bytes are 0. The third is 8, and the last one is 3, meaning it is a 3-dimensional array. And if you change this one to like train label, you can see that it is a 1-dimensional array. Okay, so we already got the dimension of the array, and we got a D type. It should be ubyte. So each value contains just 1 byte, no matter it is a label or image. Now we only want to see the size of each axis. Let's just read the last one, the dx3. Okay, file is okay. It should be image. So let's just use the tuple decomposition to get the D type, and NDIM is equal to this thing. And we should assert NDIM to be 3. We should assert D type to be 8, so that we don't have any surprise if we possibly read the wrong file or something else. Always put some assert in your scientific computation notebook or code. It will save you a lot of trouble if you have something surprise. Okay, then we should read all of these dimensions. So each dimension, the size of each dimension are 4 bytes integer. Kind of like 32-bit. 4 bytes is 32-bit integer. Except, as the remark says here, it is MSB first. If you don't know what MSB is, that's fine. But you can see it is high Indian or high. But the last sentence seems alarming because it says like in most non-Intel processors. Because we are using Intel processor, so this hints it is a format that is not nature to our Intel CPU systems. We'll deal with that later, but at least we know they are 4 bytes integer. So let's load this using np.fromFile, and let's first make them like int32, and make it show you int32 will be a little bit easier because at least we can see the hexagonal value of these integers. So because we use offset equal to 4 to skip the magic numbers, and we should read 3 of them because the dimension is 3. So let's see what it is. You can see that each of them are strange. They cannot be the dimension, the size of each dimension, because they look different. This is because MSB stands for most significant bit first. In Intel, the format of integer is Little Endian, not High Endian. So they are different. If we use so let me just put it into an array, say just A, and let's look at each element in their hex representation. So let's see HEX, X for X in A. Let's just see it. So you can see that it has a lot of 0 at the tail part, and the number is kind of, the non-zero part is almost at the beginning, at the initial second. So it's pretty much hint us that it has a wrong direction. So in fact, if you do some calculation, you can see that 1C, what is, maybe you can just 0x1C is in fact 28. The MNIST should have an image of size 28 by 28. So we should rearrange this number into the right order. So how do we do that? We can do it manually by loading this number and doing some bit-wise bit operations to shift something to the back and move something to the front. We can do that, but NumPy has the capability of reading MSD4s or high Indian integers. So we can simply use to tell the dtype so that it knows it is an integer of 4 bytes but with high Indian. It has a strange syntax. The first less than sign is telling it is actually high Indian, and I4 means it is an integer of 4 bytes. So if we put this dtype instead of INT32 or UINT32, we can get something better. Or maybe we should use the other sign. This one is little Indian and this one is big Indian, high Indian. Okay, so this sounds about right. So let's see again. You can see that, okay, we got our dimension. It looks like something like the correct things because we have a NumPy array. We already know it is UINT8 for dtype, and the shape seems to be 60,028 by 28. So it most likely it means we have 60,000 digits, 60,000 samples, and each sample is an image of 28 by 28. So that sounds about right. And you can do a similar thing for testing images and testing labels, except that testing image and testing labels only contains one dimension. So you only need to have one size instead of 3 different sizes. So let's put them together. And you can see I do sometimes some check here to see the dtype should be 8 and the dimension shouldn't be too large. So just make sure nothing surprise here. And we read everything here to see the header. And because we have checked everything is correct, like the test data have 10,000 samples, and the image should be 28 by 28, and the label should just be 10,000 numbers. And similar to the training data, except it has 60,000 samples instead of just 10,000. So everything seems correct. Then we write a small script to load the actual dataset files as a NumPy array. So this is a small function that I wrote, and we load the training data and the testing data. Just note that I reshaped these things as this shape. So I kind of flatten the image into a vector for each of the sample. Instead of making it as a 2-dimensional image, I make it just like a vector because we don't need the property of the images in our following algorithm. And also, I divide the image value by 255 so that each pixel, the intent of each pixel becomes a value between 0 to 1, something between 0 to 1, so that we can do everything in floating numbers, which is more suitable for numerical operation. Okay, we load the training data and testing data right here. So we have to see this data because they are all NumPy's ND array. So recall again, we should check the shape and the dtype. And you can see that the shape here and dtype, you should check them by yourself. But I already know the dtype that each of them are floating numbers for the image part. And for labels part, they are still UINT8. So this is a training set. It is a tuple containing the images and labels corresponding to each images. And here are some shapes here. Because we don't have validation set, so this one cannot run correctly. But for the training and testing, you can get the things as expected. Okay, now we are going to do some machine learning part. The typical machine learning problem related to this MNIST dataset is supervised learning problem, corresponding to the task of recognizing the digits from the handwritten image. So let's make our training dataset train X and train Y. So in the terminologies of supervised learning, we usually the variable that as input as X and the output of a function to be Y. So we call it train X and train Y. The reason that the X is in capital and the Y is in small case is because X is a vector, but Y is just a simple number. So I keep this file name convention to remind me the type actually the shape of these samples. So let's see our training Y first. So you can see they are just some numbers. Our first 10 elements in training Y are just numbers. They are just the integers corresponding to the digits that is written in the corresponding image. And as we can see, the X has a shape like 60,784, and of course 784 is equal to 28 times 28. And we can also see the first 20 items in the training data, and you can also check the testing data. Okay, let's get to the contents of X. To see what contains in training X and testing X, let's first write a simple script to show the image. So we can see that this is just a simple script that I use a reshape, and I can use a transpose instead, but I use swaps access and reshape. So I do some reshape things to the array so that it becomes image. And of course I do some type changing because I already convert the X as a D type of a floating number. So if I have to make it to compatible to the PIL, to the PIL, I have to first multiply it by 255 and then change the type to be unsigned integer of a bit of 1 byte. So I make a small utility function so that I can take any part of the training set image or testing set image and make them as image so that I can see them. So this is showing the image from 120 to 150. But if we only want to show the first 20 images, we can do so. You can see that in the training dataset, the first 20 images 504, 192, 1 and 3. Recall this is the corresponding label. Okay, let's also do the same thing for test X, and see the test X has this shape, and maybe we should see the first 10 elements of test Y. Okay, 72104 seems okay. Okay, we are going to use the nearest neighbor method to do the prediction or to do the recognition of digits. This is probably one of the simplest method, and probably the method you can imagine or you can think of by yourself. So what is this method? It's pretty naive. That is, think we have a training dataset that contains the 60,000 images. So say you take one of the images from the testing data, or maybe you just write it, just one image. How can I use this training data? How can I leverage this training data to help me to identify what is the number of the digits corresponding to the digits that I just written? So one simple way is, can I just try to find the most similar image in our dataset out of 60,000 images to find the most similar one? And if that one, because we already have a digit correspond to each image in the training data, so if that one is the most similar image is a 3, maybe I just make my inference or prediction that the digit I just wrote or I just taken from test data, I just predict it as 3. Maybe it has its fair chance to getting the prediction correct. Okay, so that simple method that we just described is the nearest neighbor method. The only problem is, what exactly does the similarity means? So how do we say two images similar? There are many different approaches to say two, or different metrics to measure how different or how same two images, like SSIM or LPIPs, which use the neural networks. But again, we can use a more obvious, simple, boring, naive method. So let's just use the square error that we just, or maybe you have heard it is the Euclidean distance between two images. So what is the L2 or the Euclidean distance? It is simply we compute the square difference, the sum of square difference between two vectors. So suppose we have a vector U, in this case, we take the first training image, and V, the second training image. How do we compute this square difference? So let's see the first two images. They are different, so they should have a fairly large differences. So we simply compute the difference between these two factors. So the first one is called U and second one called V. We simply compute the difference between these two factors. Recall that this operation works element-wise. So we subtract each corresponding elements, and we compute the square of each element. Then we sum them up. So if U and V are the same, the distance should be 0. And if they are more different, the value should be really large. So this is usually called Euclidean distance or L2 distance. So in fact, L2 norm is defined the square root. You can see that L2 norm is defined as the square root of x squared plus y squared. So you may say this familiar because this one is just the usual distance that we compute a plane or on two different things, two different points on a plane when you learn the geometry. Okay, so instead of using these basic operators together, we can call a function exists in NumPy library, which is in a submodule, linear algebra submodule. And the name is not surprising, it's just called the norm. So we can compute the norm. However, you can see that for a norm, it will taking a square root. So if we want to compare the sum of square, we should compute the square of its norm. They should be similar or the same. So you can see that in fact they are pretty close to each other. In numerical computation, the slightly change of the algorithm will change the value. So sometimes just because you change the order of computation, logically they are the same. But because of some rounding error, they will yield different results. So we should consider these two agree to each other, even though they have a very small differences. Okay, so the difference between train x0 and the train x1 is 87. So how large or how small it is? Let's see. We will see it and compare all of them. I mean, we should run it for more numbers to see what does it mean. So what should be a small distance and what should be a large distance. But before that, just a quick note that you don't have to use the L2 norm. You can use L1 norm right here. It also has another name that is the absolute error, the sum of absolute error, or L1 distance. So it simply compute the difference between two vectors, and we take the absolute value of each element and sum them up, and it has a name called L1 distance. We also have L3, L4, or even L2.5, or maybe L1.5 norm and the distance. So you don't have to use L2. But L2 is quite popular and have some nice properties, and we are going to use L2 in this notebook. Now we are trying to find and display the training sample that is closest to the given test sample based on the L2 distance. So let's just take an arbitrary test sample. This one is 3217. Let me just put like 4321, or just an arbitrary one. You can take anything, and we loop through all the 60,000 training data and compute the distance. And trying to find the image that has a small distance between this target image. So let's run through the loop. Then you can see that the target image in the testing data looks like this one. And we do the loop to find the best match. And every time we find a new best match, we display it. So you can kind of have a feeling and see the progress. So we have a 9.5 at the beginning. This one seems to be close enough because this one is the first image in the training data set. And as the progress advances, you can see that we got an image that's supposed to have less and less distance between the targeting image. And it actually looks getting similar to the target image. And the most similar image in a training data set of all of the 60,000 images. This image is the best match to target. They are not exactly the same. We can definitely see it, but this one is the best match. And although they are not exactly the same, the prediction seems to be correct. And we can see, just print out the best match is 9, and actually probably I should just show the ground truth. The ground truth is also 9. So this one is a hit. It is. So maybe I can just show another 1, 2, 3, 4 and do the process again. And in this case, you can see that even in a progress, some of the images does not contain the same digit, but they are quite similar. But again, in this case, we still got a hit, a correct result, and we got a pretty similar image to the target. Let me just do one more try. Or maybe I just pick like 5, 7, 1, 9. Just arbitrary, any number should just work. And in this case, both of them are 9, and our prediction is correct. So it does really seems promising. It is not that slow, because every time I just hit execute, we almost got the result instantly. It is not that fast because it still has to run the loop over 60,000 images. But out of the 3-4 experiments, it seems that it gets all those tests correct. Okay, so how can we do it, improve this algorithm? Here's a little quiz. Although I have already done it for you, but here's a little quiz. So if you really want to think about it, you can pause after I explain what this quiz is. So basically, we want to remove the loop. So using a more NumPy way to find the nearest neighbor. The loop that I mentioned is this loop, just this loop. Because we have a loop over the 60,000 sample to compute the distance. In fact, in NumPy, if we can to eliminate the loop, especially a loop that large, then it improvement. So how can we do that? In fact, we can do it by using the element-wise operation. So first of all, we can compute the distance in just one operation. We do this computation, do the subtraction to find the difference between training dataset and the test. Our target is supposed to be the first one, x0, test x0. So we can find the difference between training x and testing x0 in just one step. This can be done because of the broadcasting. So we actually find the difference between test x0, train x0, test x0, train x1, and x2 simultaneously. And we compute the square of each difference simultaneously. The only difference and we need to know about is do the summation. We don't want to sum all the elements together. We want to sum the elements for each training sample. So we have to choose one axis to do the summation. In this case, we choose the axis 1, and this guy is going to get all the distance between each of the samples and the test x0, which is the first sample in a test dataset. So instead of writing a loop that running 60,000 times, we just use this one-liner to do so. And we can also find the best match simultaneously just in one command. We use argmin. That is, we find the smallest argument. That is, find the smallest number inside this distance. And we are not trying to find the smallest distance, but we are trying to find the position that has the smallest distance. That means ARG. So we're finding the index of the sample that has the smallest distance. So we do it just now. Let me replace this 0 by target ID so that we can try different samples. So you can see in this case, target ID that will be 1111. So in this case, okay, I should put this target ID. So this one is a target and this one is the best match, and it is correct. Try the next one. Okay, we got our first wrong prediction. The correct answer should be 4, but our prediction is 6. But this mistake is understandable because these two images does have some similarity, except they just represent two different digits. this is something that we are expecting that could happen. We're just hoping that it doesn't happen too often. Okay, so we'll just try another one is also a hit, and this one is also a hit. Okay, I almost say this one is a hit, but this one is our second wrong prediction. This one should be 3, but we are predict inference it as 8, which is incorrect. But again, as you can see, these two images are quite similar. So we can understand it is something that could happen. Okay, and another one is correct. So maybe we should see how good it is. We have just a rough idea of how good or how bad, how accurate this algorithm is. But we want to actually have statistics to see the accuracy. So let's just run through the first 100 test data and see how accurate it is. So this is just a simple loop to do so. You can see that, okay, we computed distance, and for each distance we computed argmean, and if they are the same, our correctness is +1. Our n is 100, so we can see the accuracy. So, and I am also using TQDM to show the progress bar, because sometimes we are trying to run it through with larger n, so it may take some time. So it is nice if we can see the progress, so that we can decide whether we should interrupt the prediction process. So you can see, okay, for 100 number, for each number it almost instantly. But for 100 number it do take some time. We are hoping we can run it much faster. For the first 100 number, it has 100% accuracy. It is nice, but we still want to test for more numbers, more samples, so we can get a more accurate accuracy. So our goal now is to try to make it faster, so that we can test it the whole 10,000 samples in the testing dataset. So how about we get rid of the loop, just like what we did. So first of all, maybe we can using some broadcasting technique to do this U minus V. But suppose we have, like in here, we have all training data. We have 60,000 training data, and we have, like, let's just try the first 30 samples. 30 is less than 100, but to illustrate the difficulty of doing so, let me use the first 30 element as an example. So suppose we want to using the broadcasting or vector operations to do it in one go. For these 60,000 and 30 elements, how many we can actually do so, but how many results should we hold? Because we're comparing these 30 samples with these 60,000 samples, we should store 30 times 60,000 results. And each of these results, because we are trying to using U minus 1 first and taking the square, so we should get 784 elements times 60,000 samples times 30, which is a huge number. But if we really want to do so, we can do that. We need to add one more axis. I'm using reshape, but you can simply using new axis things to add new axis, expand dimension or other things. But I'm just simply reshape it here. A better way to do that is to maybe more easy way to do that is this one. But I'm going to use the original one because you can see it more easily to which dimension is which dimension. The thing is, we're adding a new axis at the beginning of the training X, so this one's new. And we are adding, not this one, 30. Okay, we are adding a new dimension. No? Okay, no, sorry, I modified it. So it should be, okay, this one is okay. So we're adding a new axis at the beginning of the training data. And we are adding, not the beginning, not at the second axis here. So this one is a new axis, and we are adding a new axis here. So just see that the 784 we are keeping them the same, but this one is 1 and this one is 30 and this one is 60,000, this is 1. So because we kind of making them the 60,000 and the 30 at different axes, so that we can get all combinations. Like we said, we're going to have the distance between each pair of the training sample and the testing sample. So they must be in different axes. And by using broadcasting, we can get the result we want. So let's do it and do a computation. It is not that fast. It still takes some time, like 10 seconds or so. How long did we take it? If we are using loop for like 100 samples, it takes like 24 seconds. But right now we are only using 30 samples. It still took a lot of time. And the reason is that it actually requires a lot of memory. So because it used too much memory, so it is not that efficient. We got it, but it is not efficient enough, and it takes a lot of memory. So it is not a very good. So you can see that U minus V is in fact okay. We probably is going to have okay. The 4 seconds is still okay, but you can see that this one is a huge array. So we can do some simple calculation. If we are trying to do this for the first 100, or not for 10,000, just for first 100 elements in the testing data, it requires 60,000 times 100 times 784 and times 4, because each 4 numbers contain, it actually contains 8 bytes, because it should be a double. But suppose we are not using the 4032, it still requires like 80 gigabytes memory. So because it used too much memory, so the efficiency is not good. At least it's not good if you want to have that memory to keep in the Python RAM. We can still do this thing, do more efficient, and you can see that for the first 30 sample we got accuracy 1, but it's just kind of too slow. It is correct, it's just too slow. So how do we bypass this limitation? A trick that we can use is that we can use the inner product. Like we talk about the matrix multiplications, they are quite useful, and they have been implemented quite efficient in NumPy. So we can use dot, because we know that the square difference is pretty similar to doing a dot inner product, a dot product. So in fact, we can translate the difference of the square norm into this formula. So we only need to compute the norm over the first vector and the norm over the second vector, and do the computation of the dot product. If we want to do a lot of dot product with pairwise product of a bunch of testing vectors and a bunch of training samples, in fact, it becomes the matrix multiplication. So we can using the Python function to do it quite efficient. So it is doable. It is doable using this method. However, right now I'm going to do a little variation of this kind of thing. Instead of computing the L2 norm, let's compute the cosine similarity, because it is still a very good measurement to the similarity of two images, and we can use just one matrix product to do so. Okay, so let me first copy the original data first, because we're going to do some process on it, and we still want to maintain the ability to show the images. So we keep a copy of the original dataset image, and then we normalize this train X and test X by their norm. So because for a cosine similarity, each factor has to be unit factor, so we first normalize all the factors in training data and in testing data. In some libraries, it contains some functions to do a normalization to make every factor become unit factor. So instead of doing the division right here, you can just using one function to do so. But this one is still a fairly way to do. Then we simply do the matrix multiplication to get the cosine similarity between the test dataset and the training dataset. And you can see that it is quite fast. It only contains like 4 seconds, and we have already done the similarity distance, computed the similarity distance, actually not a similarity, just a similarity between 10,000 testing sample and each of the 60,000 training data. So we do compute the distance in just one go. And we can use argmax, argument maxima, to find out the most similar sample in the training data for each of the testing data in just one go. That only takes like 0.4 seconds and we are done. So we can see, let's see the first several prediction here. And let's see the image of the several testing images. It looks quite okay. Let me put it just the first 20 prediction. By quite casual comparison, it seems to be correct for each of them. Or maybe we could just take the first 20 labels in the testing data and by compare the prediction and them directly. So this one is a computation for accuracy. We simply compare the prediction and ground truth in test Y. If they are true, we'll get a true, and if they are different, we'll get a false. So you can get true, a lot of true. Some of them are going to be false, but a lot of them are true. Okay, so if we take a mean, because true is usually treated as 1 and false as 0. So the mean means how many of them, what is the ratio of them in this array is to be true. So this can be translated as an accuracy. So we got 97.23% of accuracy in this test. By considering our method is just so naive and simple, and it is quite fast because we only take like 5 seconds for 10,000 to test 10,000 samples in the testing data. So it is quite easy and nice. And sometimes this sort of naive method can beat some more complicated or more advanced method, especially if you don't do it correct. Even if more advanced method can beat this method, I mean, this kind of simple method serves as a baseline so that you can judge the more advanced and the effort you put into develop a more complicated algorithm is worse or not by comparing to this baseline. Otherwise, if you get something like a 95% for your some algorithm, you probably develop it for like 2 days or 3 days and do a lot of testing, you got a 95%. You may think 95% is pretty awesome, but it is not, because we already know that using one of the most naive and simple method, we can do it 97% and very fast. So in fact, if you are using like more advanced algorithm like SVM, support vector machine, or maybe you can do it in like softmax regression, you are most likely to get it like 92-91% accuracy in most of the time. There are some way to increase the accuracy, but if you are just using a scikit-learn and okay, I just take some support vector classifier or taking some like decision tree or maybe even some like random forest, you probably are getting something less than 97%. Okay, for the rest of the notebook, we are talking about the PCA, but not today. Maybe in later lectures, we are going to see about this method. For this method, it will reduce the computation time even further, and sometimes it can improve the accuracy a little bit. Until then, have fun to try this simple method and recognize the digits in MNIST dataset.